Cast is now starting. All attendees are in listen-only mode.
All right. Good evening, everyone. My name is Hayden Frank, and welcome to the National Weather Service Boston Norton webinar. Today, we will be going over the June 1st, 2011 tornado outbreak in southern New England. Hard to believe that it's been 10 years since that event, but a lot to cover on that. Before we get into the presentation, just a few quick things. Everyone is on mute. So if you want to use the chat box for questions, we'll answer them at the end of the presentations. And all these webinars are posted on our National Weather Service Boston YouTube channel. It may take a few days to get there, but they will get on that channel. And we'd love your feedback. So you can reply right to your webinar confirmation email or to Joseph Delacarpini at NOAA.gov. And we also will do a quick weather briefing at the end for the next 1 to 2 weeks here. Okay, just a few more things to discuss before we get started. Fortunately, we are coming out of the pandemic, which is great news. But we are going to continue these public webinars. We've gotten a great response. We actually have another one coming up on Thursday. This will be discussing the 2021 Atlantic Tropical Season Outlook. And then the following next Tuesday, June 8th at 7 p.m., we're going to go over the new climate normals. We've made some adjustments based on the change in the 30-year increment there. And Tuesday, June 15th, we'll be discussing storm damage surveys, what we go about, what you look for, how we determine strength of tornadoes, if it's a tornado, microburst, those type of things. So please go to weather.gov/Boston webinars, and you can register right like you did for this one. So again, my name is Hayden Frank. I am a forecaster at the National Weather Service office in Boston Norton. And with me tonight is Bill Leatham, who will be doing the second half of the presentation. He's actually working at midnight tonight, so major props to him for coming in early tonight to help me out with this. And he actually has a model simulation of this event at the end, which will be really interesting to see. So without further ado, we'll go into the meat and potatoes here of this presentation. Hard to believe that it is the 10-year anniversary of the June 1st, 2011 tornado outbreak that really hit Massachusetts quite hard. This is look at the storm reports received from that day. Obviously, we had the long track tornado from Springfield to Munson area, but there was significant severe weather all over the Northeast, including a couple tornadoes in Maine, and then you obviously see stuff out in the Midwest. And the 2011 severe weather season was very active across a lot of the country. So this was quite the active season here. And a brief overview of what happened. Well, we had 4 tornadoes in our area in Massachusetts. One was a long track EF3 tornado. That's the one in basically from the Springfield to Sturbridge area through Munson, almost 40 miles. We had 2 EF1s and 1 EF0. Unfortunately, resulted in 3 fatalities. There were 72 injured and $175 million in property damage, damage to 1,400 houses and 78 businesses. 10,000 acres of woodlands destroyed. The most destructive tornado outbreak in Massachusetts since the Great Worcester tornado on June 9th, 1953. On the lower right of the image here, that is actually a satellite imagery of the basically all the trees uprooted along the tornado's path. That is still shown today. You can still see the damage where basically anything in the path, all the trees were completely destroyed. So again, you know, the tornado outbreak, you know, obviously a tragic event when anyone, you know, loses their life. But it was a part of a larger severe weather outbreak across the Northeast. It was a high cape, high shear environment. We actually had baseball-sized hail before the tornadoes in the Berkshires. There were reports of straight line wind damage all over the place. There actually was severe weather early in the morning, a couple storms that produced hail. You often see that sometimes very early in the mid morning, things clear out, and then you get the main event in the late afternoon to early evening hours. So what I want to do is kind of go over the basics here of what the overall pattern was going into that day. So this is a look at what we call 250 millibars, but to give you an idea, it's about 35,000 feet off the ground. So we're looking at where airplanes fly in that general sense. And what you'll see here, and we'll work our way down, but there's what we call a closed upper low, an area of say cold pool aloft, cold air aloft at that level. And then south of there, you see these barbs here. That's triangle is 50 knots. So this would actually be over 100 knots of wind coming towards the Great Lakes. Now, keep in mind, this is a good, 6 to 12 hours before the event in our region. So these wind fields would be spreading eastward as the day progressed here. And looking up at 500 millibars, again, we're I should say going further down because we're about at 18,000 feet, somewhere in that range. And this is one of the things we often see when we're looking at severe weather in the Northeast. You'll see this closed upper level low. It's what we call an area of cold air aloft at that level, and it can be roughly from the northern Great Lakes, up towards Hudson's Bay. And another thing you'll often see is a ridge of high pressure. This is actually the opposite, kind of a area of warmer air at that level to the south. And then the battle zone is going to be in this area in between, and that's where you tend to see your severe weather. So that's basically how we'd like to kind of simplify things and kind of work things down from there. So again, what we did was we actually had a student volunteer who did an excellent study for us, looking back at our severe weather events and what type of pattern we tend to have during those events. And one of the things would be that closed low. We called it a type A, a James Bay closed low. Again, it could be up here, it could be further down. It doesn't have to be exact, but the general idea is you're going to have something to the north and west, a closed upper level low to our northwest, and an upper level ridge is often helpful too, across say Texas, Arkansas, into the southeast. So going forward here, we're looking at 850 millibars. So we're working our way down into the atmosphere. So let's say we're roughly 5,000 feet. And again, this is the morning, so this is around 8 in the morning. Here are the stronger wind fields out here that are going to be moving east and set the stage for late in the afternoon and into the evening across our region. Now, one of the things I should say in terms of takeaways from this presentation, we get thunderstorms in the Northeast, in our area, obviously. We get severe weather. Most severe weather in New England, we'll have some thunderstorms move through. There could be usually a few towns hard hit. Often we're talking about, 40 to 50 mile per hour wind gusts, brief heavy rain, obviously dangerous cloud to ground lightning, a few trees down here and there. But what often is the big separator between, say, those type of events and these rare high-end events are called elevated mixed layers. And what that is hot, dry air that actually originates from the desert Southwest, and it moves east into our region. And one of the things our computer models allow us to do is kind of do a high split model. And what that is basically a backward trajectory of where the air mass came from. And we did do that for this event. And you'll see it basically that air mass in the mid levels of the atmosphere originated from the desert Southwest. And in the next slide here, this could be a little complex to the eyes here. I know it can make me dizzy, but basically the idea here we're starting ABQ, that's Albuquerque, New Mexico, and then we're heading eastward to say Albany and Nashville. So we're working our way across the country. And Usually we're, obviously the layer can differ a bit, but usually we're looking in that, say, 700 to 500 millibar area, which would be, say, 6,000 to 10,000 feet off the ground. And what you'll see is the green area is the dew point, and we're looking at this is what we call a sounding, and it's looking at the profile of the atmosphere all the way up. So we're just not looking at the ground. What's it at 10,000, 20,000 feet? And what you'll see is the red is the temperature, the green is the dew point. Look at once you get above 700 millibars, there's a large difference here in a lot of these plots between the temperature and the dew point. That's that hot, dry air that's working across the country into our region that would set the stage for this rare high-end severe weather event. Now, again, there's two ways that this kind of helps us get significant severe weather. One is it creates a strong temperature differential between 700 to 500 millibars. If we looked at that, say 18,000 feet, which is at 500 millibars roughly, you have that cold pool aloft. But you have that warm air down by 700 millibars. So you have a rapid temperature decrease from that 700 millibars to 500 millibars, or say 10,000 feet, to 5,000 feet. In that layer, temperatures are rapidly cooling, which is good for thunderstorms. They like the atmosphere to be going from hot to cold as quick as it can as you work your way up in the atmosphere. However, the elevated mixed layer, it actually creates a temporary warm layer. And we're going to look at this on the next slide. So this is the Albany sounding for 12Z June 1st, okay? So we have this dry mid-level air that's come in all the way from the desert southwest, okay? Now, we haven't had surface heating yet. It's, very early in the morning. But what you'll notice here, you have this area where the temperature isn't decreasing much with height, but then once you get above it, it starts to rapidly decrease with height again. You have to wait until this area is eroded to get surface thunderstorms, to get those real strong thunderstorms. Often, if we don't have an elevated mixed layer, you actually could get thunderstorms a lot earlier. You can actually get many more of them, but it's like competition. The earlier they develop, the less heating you can be realized. So the thunderstorms that develop, they may be more of them, but they tend to be weaker. So it can be counterintuitive in some way, but when you think about it, it makes sense. So Albany actually launched a special sounding 3 hours later. This was 15Z, and you can see now you're starting to get the heating. And because of this elevated mixed layer, those of you who are familiar with instability in CAPE, we often talk about. A lot of times when we're talking about our severe weather events in New England, we're talking about 1 to 2,000 joules of CAPE. Well, by late morning, there's already about 3,500 joules of CAPE. So that gives you an idea, those steep lapse rates, how they can generate that instability. And also notice the turning with the wind as you work up in height, okay? You're, working up, the wind's at south at the surface, and you're going west as you go up in the atmosphere. Well, tornadoes like that environment. They like that turning with height. If you have unidirectional winds where they're more from one direction, it's more difficult for tornadoes to develop. So I, can't stress enough the amazing job the Storm Prediction Center did with this event. It's very rare for the Northeast to be included in a severe weather outlook beyond 3 days because we just don't usually have that elevated mixed layer. So the confidence in widespread severe weather, significant severe weather, is normally not that high. But in this case, they saw the ingredients and they put a day 5 outlook for the Northeast, which is very unusual. So, a big kudos to them. And as we got towards day 4, again, so this would be, over the weekend, they still have this highlighted, they're talking about high dew points, and they're talking about a cap. You get that cap when you have that elevated mixed layer in place. And also you have wind fields, the strong wind fields with that. Remember we talked about that low near the Great Lakes or just north of there. So that's favorable to bring those wind fields into southern New England. And this is just kind of honing it down a little bit as we get towards day 3. This middle graphic here is indicating where the severe weather probs are. So the whole area is under a risk for severe weather, but you can see the highest risk is northwest of, say, the I-95 corridor. Obviously, that's right where the major tornado occurred. And as we kind of work down, this is a day 2, and obviously a big slight risk. SBC's actually tweaked their categories since then, so there are more categories now. So you likely would have seen somewhere an enhanced outlook probably by now, if that setup was in place today. Maybe even a moderate, because we have so many more data sets available. A lot of data that we look at to evaluate severe weather, including high resolution models, weren't even available then. So again, that reflects to the great job they did with this event here. And as we got into the day 1 outlook here, you can see the probabilities of tornado. That's pretty high for this area. You don't usually see a 5% highlight in our region. So that gives you an idea of their confidence level, and they were able to maintain that into the afternoon there. So one thing that they will also do is provide these mesoscale discussions. So you have the forecast models you're evaluating, and then you're evaluating near-term conditions, what's going on. Are storms developing to the west? Is there more cloud cover than we expected? Is this instability higher than we expected? Is it lower than we expected? And they'll kind of give a hint on what they're thinking. So in this case, they're talking about northern PA and New York. This is just after 8:30 in the morning, and they're basically saying, severe potential, watch likely to be needed soon. And that trend continued, where they did issue a severe thunderstorm watch to our west. Again, this is went into effect in the morning, and then expired around 5 in the afternoon. Out west, obviously, they were getting into this earlier and getting out of it earlier. And they went with a severe thunderstorm watch in that area. And as we go east, we'll kind of look at a few things as to why they went with a certain product that they did once it got towards us. So what you'll see here, this is around lunchtime. We're getting close to lunchtime. You have this frontal system. You have on the visible satellite, these puffy clouds developing, and then you see these are actual blow off from thunderstorms developing. And our satellite resolution is also much higher than it was 10 years ago. We can get the data almost instantaneously. So you'd actually be looking at more precise data, which would even help more. But what you'll notice in southern New England, I remember we mentioned we had a few early morning thunderstorms, and they slid off the coast in the morning, but you don't see any real, cumulus clouds. There's some low clouds with a, warm flow off the ocean, but those aren't really, what you'd look at through thunderstorms. You really don't see anything out until you get, you're looking into Vermont in that area. So remember I talked about that mid-level warmth, that stable area? Well, that was going to kind of keep you from developing thunderstorms too early and limiting your instability later in the day. In this case, we were allowed to develop the instability because of that warmth, that mid-level cap that was going to keep things at bay, but when things fired, they were going to go explosive. Okay, so looking at the mesoscale discussion here, this was issued just around lunchtime here concerning severe thunderstorm watch. They were actually expecting a severe weather threat to develop further east now. And notice up here, they mentioned tornadoes, isolated large hail damaging wind gusts will be possible with the stronger cells. Another watch will be issued within the next 1 to 2 hours. And look at the Cape values. Again, remember I said we're usually 1,000 to 2,000. Well, in this case, we're already 3,000 to 4,000. And deep layer shear, there's usually you want it for a major severe weather outbreak, you're looking at 35, 40 knots, and that's right where we were in that deep layer shear, because You also need not only the elevated mixed layer, but you're looking at for at least modest wind fields. They don't have to be crazy, but they have to be relatively modest. And you can compensate if you have more instability. You can kind of get away with less wind, vice versa. So that's kind of how it was evaluated. But again, they did an excellent job here. And this was issued from at 1 p.m. And you can see a tornado watch box from basically the Philadelphia area through New York City, up through Boston, through Portland, obviously including areas east of the Berkshires there. So really highlighted the area. And you can see here, this was the severe thunderstorm watch. And the reason they opted to go with the tornado watch is because there was more turning with the wind with height in our region. Remember I said the winds, when they're uniform, there's less risk for a tornado. When they start to turn with height, if you're due south at the surface and then go west just off the ground, that can be very conducive for tornadic development if you have enough instability. And then they were looking at the severe weather threat expanding even further into Maine. So they were going to expand the watch. This is just after 1 p.m. And remember, the instability wasn't quite as high, but they actually had better wind fields. You can see up here, the wind fields were even stronger. Each triangle represents 50 knots. So there's a lot of, pieces that you, put together when you're forecasting severe weather. So with that, I am going to turn it over to Bill Leatham, who's kind of going to go into the radar data, more of the mesoanalysis, the real near-term stuff, and then look at a simulation he ran for this event. So, Bill, do you want to take it from here, and I can give you control?
Sure.
All right, I'm going to stop showing my screen here.
Do you have to change the presenter to so I can
Let's see. I stopped showing my screen. Can you
no, it's not giving me the option to it's just can you
I see it now.
Okay, all right, let's get going here. Sorry for the delay, just a little popcorn break for folks. Where is it? All right. So as Hayden kind of said, I'm going to cover more of the radar and mesoanalysis, and this is something that anytime we've got severe or any office in the country really has severe weather, this is the stuff that we take a look at when we're in the process of deciding if we're going to put out warnings. All the different things kind of that are going on in our mind on top of all the forecast information that Hayden kind of passed along. So at 3 o'clock here, you can see in the bottom right hand side of the screen, there's this surface weather map across much of New England, and you can see for any time of year for New England, this is pretty warm and moist environment with temperatures in the upper 80s to low 90s with dew points in the lower to mid 70s, although a little bit cooler, as Hayden was alluding to, once you get out into eastern Massachusetts. And then maybe unsurprisingly, as Hayden was showing, we're getting to the point where we had a watch up. You can see that there's some various different thunderstorms across the region. And for us, of course, since our responsibility, Southern New England, we were focusing on the stuff heading in from the Berkshires. So as I kind of talked about, when we're kind of taking into account of what kind of warnings and that we put out, we take a look heavily at the SPC mesoanalysis page, and this is a couple things that folks would take a look at to determine if the environment is tornadic or not. In the top left-hand corner, you can see that this is kind of as Hayden had said, there's lots of instability with 3,000 to 4,000 joules of CAPE And then the other thing that's shown in the background there is shear, because shear is also important when it comes to supercell thunderstorm development. And usually you get anything over 40 knots generally is a good cutoff. And you can see with those wind barbs there, most locations are at 40, if not 50 knots in some spots. Another thing too, if you look at the middle, in the middle here, the 0 to 1 kilometer storm relative helicity, it's usually when we have anything over roughly like 150. That's when you're starting to get worried. I mean, even lower values you can get stuff, but once you start getting higher, it can indicate, potentially stronger storms. In addition to the storm motion that's on there, the estimated helicity index, which is a combination of the energy helicity index. It's an index between helicity and how much instability you've got, and you can see that it's kind of highlighting 4 to 5 in the 0 to 1 kilometer layer. So that's saying that there's definitely a risk. Then the significant tornado parameter here in the bottom. So when it comes to violent tornadoes, if you look at like the definition of the significant tornado parameter, they tend to happen with values usually anywhere over 1. And you can kind of see once you get into southern New England and into western Massachusetts and northern Connecticut, we got values near 4. And then again showing kind of the reflectivity across much of New England around 3 o'clock. All right, so going a little further in time at 4:06 p.m. So the image on the left here is a typical radar reflectivity image, and you can see that these storms have progressed a bit further east. And you can see here there's some supercellular structures. The one way you can kind of tell that is looking at the right hand side here, which is the storm relative velocity, which is going to give you an idea of what the storm relative motion within the storms are. And if you look here, you can see a lot of these greens and reds next to each other, indicating that there's like a mesocyclone, and that's what's indicative of determining something is a supercell thunderstorm. And you can even see stuff when you're getting into New Hampshire and in southern Vermont. Even there might be some weak rotation with some of these other systems, but obviously the one that we're focusing on for this particular situation, you can see this storm right in western Hampden County. So prior to the tornado that happened in Springfield, we had a couple different tornado warnings, 3 that had been issued up to this point in time, getting to, like I said, we're at 4 o'clock. However, we didn't have any reports of wind damage, funnel clouds, or tornadoes, and that's when it comes to us issuing warnings in the office, it's kind of one of the, like, we have like it's almost like a weighting scale. If you're sometimes when you're not getting reports, it can that sometimes makes it tougher to put out a warning potentially, but it's a combination of a lot of different things. But up to this point in time, we had 3 tornado warnings that we put out, but there was no, like as it says here, no reports of wind damage, funnel clouds, or tornadoes. So again, as I alluded to in the previous radar slide with the velocity, you could see that storm over Hampton County moving further east, and you could see the rotation with the mesocyclone associated with that storm getting more intense, and you can even see it again a little bit further in time. It's getting even more intense. Now, the difference between these 2 images here is the one on the left-hand side is the radar from the Albany office, and then the one on the right-hand side is the radar from our office. So we do use multiple radars to get a view of the storm. And in this instance, as you can see pretty clearly, is that the radar in Albany is doing a better job at sampling the system than ours was because it's kind of on the edge of where the velocity data is a little bit tougher to discern what's going on. But you can see here around this time frame is when we put out a severe thunderstorm warning until 5 p.m. And we did mention in the warning too that there is weak rotation within the storm, and given that there was a tornado watch out, obviously that there's the potential for that a tornado could develop. So SBC frequently does updates to kind of get an idea or give the offices a heads up of what they're thinking is going on with the thunderstorm environment. And we also have folks within the office that also will look at this stuff as well to kind of do like more of a localized look at what's going on in the area. But SBC produces the best products that we can kind of show. And you can see here, as Hayden kind of alluded to, we still had a high amount of instability with 3,000 plus joules of CAPE. And you can see here they even mention in their risk that there's an enhanced tornado threat and possibly a strong tornado in Connecticut and into western and parts of central Massachusetts. And they do even mention too that there's already several well-developed supercells across the area, and they talk about several different things that they're looking at where there's an environment favorable for supercells with and possibly some intense storms and maybe even some strong tornadoes. So one other thing that we rely on in the office on top of looking at data and storm reports is that we are in pretty constant contact with various different folks, emergency managers, media folks, and what's called NWS chat. And that information can really help us on top of the warning, on top of the information that that folks call in. But having like a someone that we can kind of talk to in our chat room of what they see, what's going on, or if they have a different camera angle that we're not necessarily looking at in our office, they can give us various information. And so you can kind of see here what information was given to us over time as the tornado was developing, as the funnel cloud was developing, and as it was starting to become a tornado, as it was getting into Springfield. And so you can kind of see the chat. I'm not going to read through all the different stuff here, but you can kind of take a look at it. But then you can see on the right, here's one of the camera images of the tornado as it's from WWLP TV. All right, so at this point in time, we also had, when talking amongst the media folks, and then also based on the radar data, this is getting to 4:30 p.m. We put out the tornado warning until 5:15. And you can see here, there's an algorithm on the radars that will tell you when there's like a mesoscale, mesocyclone, which is basically large. It's usually what helps develop the tornado, or it is what helps develop the tornado. But it's the rotation that's going on higher aloft, and you can see here with this green circle is showing you that there's intense rotation. And so Hayden kind of alluded to as well that the wind's turning with height. This is just kind of another way to take a look at that. These are called hodographs, and what they do is it tells you how the wind speed and direction is changing with height. Now, when you have storms that tend to move more, what we call right-moving storms, you tend to have a hodograph that kind of looks, they both look pretty much the same, where we call it like almost like a sickle shape. And that's where storms tend to move more to the right. If it was a sickle shape, but going to like a left, moving towards the left, that'd be more left moving storms. But you can see here, what it also can tell us as well, and when we modify it with our radar data and what's going on at like a nearby airport, and this is from the Barnes Airport, we can also get information about the storm relative helicity, which we were kind of talking about earlier on when we were looking at the helicity information. Anything over 150 is really good for tornadoes. And you're looking here, this is as this supercell is passing just north of the Barnes Airport, and we're getting values over 300 meters squared per second squared, which is a lot. So this is at 4:36. Looking at the radar data again, you can start to see, you've got the rotation obviously still on this storm, and you can even see in the reflectivity, you're starting to see almost like a debris ball signature. So now here's another update from the Storm Prediction Center. They're taking a look at expanding the threat for severe storms further east. Ongoing convections, including classic supercells. They're thinking that the threat for elevated convection will happen along the coastline, at least elevated convection. So they weren't thinking maybe necessarily that there could be tornadoes, but they were still thinking of expanding it further eastward. But they were in coordination with the Taunton office at the time. So getting to 5 o'clock, again, reflectivity on the left and velocity or storm relative velocity on the right. You can see clearly what you've got, this debris ball signature on the radar, reflectivity, and with really strong rotation with that supercell. And you can even start seeing some rotation even with this storm to the north, but obviously the one that all eyes are kind of honed in on, and what this presentation's about is this storm in eastern Hampton County at this point in time. Going forward, you can see the rotation is still pretty strong even at 5:13, again with that debris ball signature. And then once you get to 5:27, we still got a little bit of rotation with the storm as it's getting into southern, south central Worcester County. But the rotation is weakened significantly. I'm going to go back one slide. You can see there's a difference between 5:13, and you can see how strong that rotation is with how with the lighter blue colors and the darker red, and then you can see we're starting to get closer to the lower values once we get to 5:27. So as Hayden kind of alluded to, I ran I'm a big fan of running computer model simulations of these kind of events to see how well they do, and to also get an idea, to get a better idea of the storm scale environment. To get into more information into what happened with the storms. So what I did is I ran a weather model on this event to see how well it simulated what happened. So one thing I always like to do when I do this is on the top is the SPC mesoanalysis information on a couple of the several different things that we were talking about earlier, and then on the bottom is the model simulated for those same parameters. So I'm just going to use one or two of them just for comparison. So if you look at the Mosaic radar composite where the reflectivity, this is right around 3 o'clock. You could see that in my model simulation, it's got a pretty good idea of what's happening. Things might be a little bit too far east in comparison to what actually happened, but it's got an overall it's doing a decent job. And then if we look at like the significant tornado parameter, given how high a resolution the model is, it's a little bit more noisy, but you can see we are getting into those bigger values of 1 to 3, even in some little spots of 4 when we're in western Massachusetts and into northern Connecticut. So overall, just looking at those couple things, we'd say it's not doing too bad of a job. So we can use it to try to get an idea of what's going on in the environment, and it's an okay simulation of what happened. And so here's looking at on the right hand side is the model simulated radar, and these aren't at the exact same speed because there's not as many images, and then the actual radar data on the left. And you can see it's not going to have the exact same structure, but it's got the overall right idea of what we call discrete storms, which is it's all these several storms that aren't very much together, and it's got the general idea of what happened right. And so as Hayden kind of talked about earlier, the couple things that you need for thunderstorm development, you always need moisture and lift, wind shear, and instability. And so the moisture and lift is kind of shown. What we had, that trough that was coming in from upstate New York on this image, and then you could see with the purple, more you're getting into the purple colors, you're getting dew points into the lower to middle 70s, and even in some spots getting into the upper 70s from the model. On the right, if you're getting any colors in the darker blue or purple, you're starting to get towards that 40 knot wind shear threshold that I was talking about, which is usually what we kind of use to help delineate between what's a supercell thunderstorm and where it's maybe not as much of a supercell thunderstorm. And then on the bottom here, you can see there's two different ways I'm showing instability. The one's the most unstable cape, and then the other is the mixed layer cape. And this is the mixed layer cape's more what we would look at to kind of get an idea of the supercell, what the supercell would be ingesting in the environment. And we're getting values of 3,000 to 4,000, which was, as we were looking at the SPC mesoanalysis, matched up pretty well. And then these little dark gray would be mixed layer sin, which is kind of like that idea Hayden had talked about, a cap. And we saw that there was one a little bit earlier, but as we go on in time, you see that it erodes here, and we've just got the instability to work with, unless you go further east, which is why they were saying that storms might be more elevated, is because there was more of a cap in place. And then going into like the low and mid-level lapse rates, I'm just going to look at to talk about the mid-level lapse rates here. As we kind of noted, when you have that elevated mix layer, and you can kind of see it here with those values above 7, that's where we really, when we're really getting into some into problems with severe storms up in our neck of the woods, anywhere from 6.5 to 7, but the higher the better. And obviously in this instance, it was more than sufficient for maintaining thunderstorm updrafts. And then looking at the 0 to 1 storm relative helicity information from the model, again, if you look into the darker green colors, that's when you're getting up to that like 150 range that I talked about earlier, and the higher the better. And as you go on in time here, you can see that those values increase, going from, this is 1 o'clock, this is 3, and then you're getting into later. So you could see that those storm relative helicity values really increased. And then lastly, just showing here the lifted condensation level. These values, the darker the color, the darker the blue, the better for a tornado environment. As you get into these warmer colors, it's getting worse for a tornado environment. And you can see here, most of the simulation that I had here, it was more than sufficient for tornadoes until you get towards the very end. And then Hayden kind of alluded to he was looking at the sounding information for Albany. So what I did with the model information was grabbed a model simulated sounding very close to where the Springfield, at Westfield Barnes Regional Airport. And there's a couple different, there's several different things that it shows here. But as you go on in time, once this starts to loop again, you can see that we've got these really high mid-level lapse rates. We've got more than enough storm relative helicity. Once you get above that 150, this is saying there's like 250. That's more than sufficient for tornadoes. And then you can even see here on the top right-hand side, there's the hodograph, and you can see that you're getting the sickle shape, which is more favorable for right-moving storms, which is what happened this day. And so one of the things that we look at in the office to kind of some of the different conceptual models of when we're trying to think about warnings and the environment. So the left-hand side shows the different near storm environment information that we have. A couple of them I kind of mentioned. If you had the effective layer, significant tornado parameter greater than 1, the effective bulk wind difference or the bulk wind shear of around 39 knots, or usually use 40, the storm relative helicity over 100, those lifted condensation levels being below 1,000 meters, which is one of the images I showed. And you can kind of see here all the different near storm environment information, and then these are going into some other types that we look at, but for this case, this was the one that we were with a mesocyclonic or supercell supercell tornado environment. And then you can see here when you're looking at radar, this is kind of going into some of the different signatures that we would look at when we're determining if we're going to put out a warning or not. And then the last one that I kind of wanted to show from the model simulation was this is the simulated infrared ray, or basically simulated satellite imagery of the storms as they cross, and this is for every 5 minutes, and you can see it did a pretty good job of the storms as they're progressing through. It even had if it starts to loop again, it even had the convection that was happening earlier in the day at the very start of the loop. So usually after all of these events or many of these events, we try to learn what we did wrong, what we did right, and try to get better, or continue to improve on what we've done really well. And so from this event, there's some best practices that our office had here. We have our Skywarn operations that had the first verified report of the tornado, and they had continuous reports as it was on the ground. We didn't show it here in the presentation, but we do have several different TV screens in our office, which we have a situational awareness display, and we can put on live news coverage that's keeping the live news coverage on in these kind of events is really good. As we showed earlier on, you could see that imagery had the first tornado on the ground, and then we did a live NOAA weather radio broadcast around 4:30 with the severe weather statement about the tornado. And then you can see here's some follow-up actions. The raise forecaster awareness of the higher end tornado events, and that's where we use that climatology that Hayden had talked about. And then you can kind of read through some of the rest here. Have a formal severe weather operations plan develop in a mesoanalyst position to kind of augment what the Storm Prediction Center is putting out, and to kind of hone in on what's going on locally. And what we have improved decision support services to some of the various partners that we've had, and we've had some different meetings to have meetings with folks about how to improve our support to these people. And so with that, I guess we have any questions, and Hayden, you can help me here with answering some of these questions if you can still hear me.
Yeah, great job, Bill. I actually got disconnected for about 2 minutes there, but must be a hiccup in my internet. I'm back.
Good.
So yeah, should we start to hammer away at some of these questions? I can start reading them, and we can take turns answering them.
Sounds good.
All right. So one here I have from John. Are there other capping mechanisms in New England beyond hot, dry, high pressure from the U.S. Southwest? Well, it doesn't have to be specifically from there. It could be, just north of there. It's really like that hot, dry air, though, that tends to come out off the desert Southwest. So in reality, it could be north, it could be a bit south of there. But the only real area to advect it from is the Southwest, because you need that dry desert air to advect in to get that mid-level cap. And why it's so rare is because it's rare to get it to advect all the way across the country. A lot easier, obviously, to get it halfway across the country into like Kansas, Oklahoma, Missouri, those states. So hopefully that answers your question there. And looks like we've got one here from Dave. Are we only concerned about turning of wind directional shear from 850 millibars down to the surface for predicting tornado genesis? Bill, you want to take that one?
Yeah, I mean, I'd say the reason that we're kind of concerned about it is because the closer to the surface, that's where these things, tend to develop. So that's usually, kind of the area we look at, but we also do look at, deeper in the atmosphere, because you need, just because there's stuff going on in the lower levels, you also, still need sufficient, you know, sufficient shear as you go higher up. But it really, for these kind of scenarios, you want it kind of in a deeper layer. But there's some other situations where you don't necessarily need it in a deeper layer.
Yeah, unfortunately, it's one of those things. There's no golden bullet or no, specific rule. You need this, you need that. It's kind of, somewhat of a balancing act. But definitely, like, the lower the turning is, the better, the closer to the ground. So the next question I have is from Rachel. Can you explain the significance of mesoscale values? So I know Bill talked quite a bit about some parameters we look at. Basically, when we say mesoscale, we're looking at a smaller scale in terms of meteorology. If we're, for example, if we're saying that there's a cold front approaching western and central Massachusetts, which is favorable for severe thunderstorms tomorrow. And then we may say on the mesoscale, there's an area of, say, high instability from the Springfield area to Hartford. So kind of narrowing it down into a smaller scale. There's no specific scale we're talking about, but when you go synoptic, it's going to be like a larger scale, maybe the whole, say, Northeast, and then you get down to the mesoscale, maybe you're focused in on, say, the Connecticut River Valley. All right. So the next question is from Dave here. Does the upper level ridge have to be placed in the deep south as it was 10 years ago, or can it be a Bermuda type high to generate the highest chance for tornadoes? Well, I will say that there's no specific rule. There's a lot of factors that come into play. We actually have plenty of tornadoes that occur without an elevated mixed layer.
Mm-hmm.
So it's quite a bit of things that we have to consider. Usually, it could be in the central plains. The ridge could be in the southeast. Normally, you want that upper level ridge somewhere to the south of northeast.
Yeah,
Right.
And Hayden, as you were saying before that too on the previous question, that's why, we also take a look at like the meso scale, because that's where we really have the risk. And like you were saying earlier, there's no real golden bullet that kind of captures everything, unfortunately.
Great. So let's see, moving right along here. Great job. And then we have another one. Um, Actually, this is from Christina. Great presentation. What is the benefit of doing a live no weather radio broadcast? Bill, you wanna take a stab at that one?
Well, I mean, I think, well, because so I don't know if that's something we still do now because that was also a different era of NOAA weather radio for us. But I think you know what it would do is since it's such a different voice that's coming through, you can probably alerts people a little more because you're not getting the typical tone. Um, and then the other thing too is, if information comes in as a person is reading it, they can, you can kind of say it as it's coming in. But I don't know. I'm not 100% sure here, but I know, it's been a while since we've. I mean, I know we could still do it, but I don't know if that was something we would still typically do.
Yeah, it's actually a good question to think about. Probably for a lot of offices in the Northeast, technology, obviously, in the last 10 years, if you look at how many people had um, you know smartphones back in 2011 versus now. So there's so many more ways to get information, and we have the we alerts, which automatically um, you know would alert cell phones for tornado warning. So yeah, that's definitely something we should think about here. So great question. And then it looks like we've got a question here from Sebastian. I have two quick questions. First, do we have any idea what some of the peak gate-to-gate velocity values were for the Springfield tornado? Second, what are the best color curves to use when dealing with New England's area severe storms and tornadoes? Well, I do know at one point, I think the gate-to-gate was basically 100 knots or so. And as for the color curves, I don't really have an answer for that one. I think it's um,
You can find a lot of good
forecaster
stuff on it.
discretion.
Google. If you did a Google search, you could probably find some, but really depends on how you're looking at it. You're kind of limited to by what software you're using.
Yeah, and I think different people like to look at different color curves, and what stands out to one person may not to another. So I think, I mean, for me personally, I definitely, the contrast in colors, makes it easier to, um, see something. But again, you're, still whatever you're looking at, you're still sampling the same value. So whatever works best uh, for each individual. And then looks like we've got to go through these a few more real quick in terms of Landon asking about some research projects. Yeah, I would definitely send an email to Joseph Della Carpini. He's our science and operations officer, and he can direct you from there. But yeah, we love research. That's how we learn from these events. So I'll go through. Let's see. We have how often do we see James Bay upper low or low with southerly high pressure? Fortunately, we don't see it too often in that exact setup,
Hmm.
but we tend to see that basic configuration, not the exact configuration, but the basic configuration when we do have our severe weather events, even if it's not a high-end event with an elevated mixed layer in place. Um, and then we've got a comparison. How would the June 1st, 2011 compare with the June 9th, 1953 event in terms of CAPE and instability? That's from Carrie. I think very similar. The June 9th, was somewhat more robust, especially with there were several significant tornadoes with that event. And obviously the population was a lot smaller back then. but the idea was generally the same. We basically had that elevated mixed layer in place, which led to the devastation in Worcester. So I think we've answered most of these. Do you see anything, Bill, that we need to?
Mm, I don't. I don't think so. And I will say, Carrie, on that question that you had too, stay tuned because that's an event I've been wanting to do a modeling simulation of as well. So stay tuned there. We might see that in the future.
Yeah, I see. Let's see. I think one more was the breaching of the elevated mixed layer cap, the main reason for thunderstorm development. That's from John. Well, it was a factor in allowing for the explosive thunderstorm development. The cold front is what triggered the thunderstorms, but the environment in place allowed them to become extreme for at least for this part of the country.
Mhm.
Um, and then there's one more from Caden about did we have a tornado emergency in effect? We did not at the time, um, and I think that's something that, given the ability now to even get more up-to-date reports, given the technology, given all the spotters and reports, that would be something that may happen in a situation like that if it were to happen today. Hopefully, not anytime soon. Um, and I think we got most of them here.
Yeah, and
So
if there's any questions that we didn't answer to, just because I know Hayden probably we want to get on with the weather briefing, but feel free, like Hayden said at the beginning of the presentation, reach out to Joe, and we can really we can probably give you even more detailed answer than maybe we can on the webinar here. So always feel free to shoot Joe even if you have any questions.
yeah, that sounds like a plan, and I can
Do you
give
want
a brief overview. I don't know if you have anything pulled up at the office there, Bill.
Nah,
Uh,
don't. Do you want me to stop showing the screen so you can?
yeah, that'd be good. Let me call up a few things real quick here.
All right, you should be able to show your screen now.
Okay, I'm just pulling a few things up real quick here. All right, bear with me one more minute here.
While you're searching, I'll see if there's any other questions here. I'll try to go through them while you're doing that and see if there's anything. Um, yeah, Carrie, the question that you had about the James Bay Low on June 9th, 1953, it could have been a factor. We honestly, we'd have to take a look at the data. It's definitely not out of the question, but there's that James Bay Low was one of the things that research had found from our office, but there were a couple other scenarios. I don't I'd have to take a look at the data. I don't have it in front of me, but that's not out of the question for the June 9th, 1953 tornado case that was a potential factor, but we'd have to look at it.
Okay, I'm gonna see if I can share my screen here. Let me know if you can see anything, Bill.
Let's.
It's
I've got a black screen up right now.
okay. I think I have to change presenter.
Oh yeah, hang on. There we go. Let me do that. Yep, there you go. Now I see your screen.
Okay, so I know we're running a little bit late on time here, so we'll kind of do a quick overview here. Let me move some things around. And can everyone see Bill, the pivotal weather site?
Yeah, I can see it, Hayden. So you're good.
Okay, so we're actually looking at that 500 millibar plot that we often looked at for severe weather. But this time we're kind of going to look in the long range. This is from one of our computer models, and it's from the GFS model, but it's an ensemble. And what we'll do here is kind of look and step through these fields here at 500 millibars, and this will give an idea of what the overall pattern is. So we're basically starting with this afternoon, and I'm going to scroll through here real quick and notice where the upper level flow is coming from as we kind of move along here and we get into early next week. Notice we were talking about that ridge of high pressure. So if you look, I'm going back now to the present time, but there's a ridge off the southeast coast. And as we move along, we're about 84 hours out. Now we're about 4 days out. You can see this is valid Saturday morning. As we get into later into the weekend, that ridging is building right into our area through early next week. Okay, so look at this. You have a big ridge of high pressure. When you have a ridge of high pressure, that's signaling usually above normal temperatures, warm temperatures. Now, in terms of severe weather, is this the greatest setup for it? No. The reason is, look where all your wind is. It's way up north, okay? We're kind of in this upper level ridge. But what it does mean is after what we had over the Memorial Day weekend, a significant change in the overall weather pattern. And this is actually the outlook from the Climate Prediction Center. And this is from June 9th to June 15th. And notice it's giving high confidence of above normal temperatures all across the Midwest into the Northeast. So there's a good chance temperatures may be pushing 90 Sunday into early next week, and maybe even over it for a day or two. So quite the change to summer weather. And I don't think too many people are going to be complaining after what we had experienced over the weekend. So I know that has been short briefing, but we will do another briefing on our next webinar, which is for Thursday, which will be reviewing the taking a look at the actual outlook for the 2021 tropical season. So please register for that. And Bill, do you have anything to close on there?
No, the only other thing I might add to The other presentation that folks might find particularly interesting, I think it was June 15th that you had at the beginning of the webinar, Hayden. It's talking about the damage surveys that we do. And I think that on the 15th, they're actually going to talk about some of the Springfield tornado damage survey stuff that we did. So stay tuned.
Yeah, that should be really interesting. And I want to thank everyone for attending, and please feel free to email Joseph Della Carpini, or just reply back to the webinar form that you got. And we always like to hear your feedback, and hope you enjoyed the presentation, and look forward to see many of you Thursday evening. So big thanks to Bill. I know, got to let him get started on the mid-shift forecast here. So thank you, everyone, and have a good evening.
Thanks, everybody.